we're going to start taking a look at transformations of the graphs of sine and cosine. So I've got a problem up here on the board. We're asked to graph on the same pair of axes, sine x and 2 sine x. So sine x, we should be familiar with. I'm going to just mark off my quadrantal angles for one period. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. I know the high value is 1, and the low value is -1. And sine, remember, is the one that passes through the origin and then goes up. So at pi over 2, we're at 1. At pi, we're back down at 0. 3 pi over 2 is a low value at -1. And 2 pi, we're back at 0. All right. And then I just connect the dots and make sure that I include these arrows to indicate that that pattern continues. Okay. Now, if I'm sketching y equals 2 sine x, since I'm doing that on the same axes, I'm going to switch to a red pen for that. Now, this is going to be a transformation. And if I do my usual, creating a little table where I list what I would do to evaluate the function and the corresponding transformation, I can see if I had an x value, I would first plug it into sine, and then I would multiply by 2. So sine of x, that's my parent function. I'm doing the multiplication by 2 after the parent function, so that tells me this is going to be a vertical change, and I know that that's just a vertical stretch by a factor of 2. Okay. So I'm basically going to be doing literally what I'm doing here to my y values. I'm just going to be multiplying them by 2. So I'm going to keep these same crucial points. Doubling 0, I still get 0. But if I double the y value here, doubling 1 is going to make the high value now be 2. At this point, our y value was 0. Doubling that, it's still at 0. This point was at a low of -1. Doubling that will bring it down to -2. And then 0 will stay at 0. So I plotted the 5, what I call important points for one period, and I connect the dots, and we can see this is in fact a vertical stretch. We've simply made everything twice as high as it was previously. Now, with this being just one transformation, you may not have found it necessary to create this table of values. And that's, or not table of values, this table listing what you did and the corresponding transformations. That's totally fine. If you find it helpful, it's a tool that you can use. And I wanted to remind you about that because I wanted to tie it in with the transformations that we've studied previously. We're just applying those skills now to this new family of functions, the trig functions. But if you're comfortable saying, hey, that's stretching by a factor of 2 and going right to the graph, I'm fine with that. Okay. All right, then we're asked these two questions. What's the amplitude of y equals 2 sine x, and what's the period? Well, the amplitude, remember, is the vertical distance between the high value and the middle value. So that's just going to be 2. Notice that's the number that we multiplied by in this particular case. Now, it is significant that we multiplied by a positive number because amplitude is a distance. It's always positive. Okay. What's the period? Well, that didn't change. That's 2 pi. And it makes sense that a vertical transformation would not affect the period because the period is the horizontal distance it takes for my function to do its thing once. So vertical transformations will affect the amplitude, possibly, but not the period. Okay. All right. So I'm going to give you folks one to try. Basically, same directions here and same questions. I want you to try graphing on the same pair of axes, y equals cosine x, and then y equals -1/2 cosine of x. Okay. So do notice we're multiplying by a negative number here. See if you remember what that means. And then tell me what the amplitude is of this transformed function, -1/2 cosine x, and what's the period. So answer those two questions for this function. Pause the video, work that out, then we'll go over it together. I've started the problem up here. So I've graphed cosine, which is our parent function, and I did go ahead and create this little table. In evaluating this, I would first take x and plug it into cosine, and then multiply by negative 1/2. Since I'm doing that after the parent function, that's a vertical change, and multiplying by a negative number is going to flip things. So the negative flips, the 1/2 is going to shrink. So this is actually accomplishing two things. It's a vertical flip and a shrink by a factor of 1/2. Okay. So I'm going to accomplish both of those by doing exactly what I'm doing in evaluating the function to my y values. So the y value here was 1. If I multiply that by negative 1, it's going to bump to negative 1/2. The y value at this next important point was 0. Multiplying that by negative 1/2 does not move it. That point's going to still be there. The y value here was negative 1. Multiplying that by negative 1/2 is going to bump it up to positive 1/2. 0 will stay at 0, and 1 becomes a negative 1/2. So now I can connect these dots, and I can see instead of starting at a high point, we start at a low point, and our graph looks like it's just half as tall. That's going to be important. What's the amplitude? It's the vertical distance between a high point and a midpoint. That's 1/2. Notice that's the absolute value of the number that I was multiplying by. Okay. So it's not just the number that I'm multiplying by, it's the absolute value. And what's the period? Well, the period is still 2 pi. Whoops. I don't want to say equals. The period is equal to 2 pi. Okay. That didn't change because this was a vertical transformation. As a general rule, if I'm working with a multiple of sine or cosine, y equals a cosine x, or y equals a sine x, I can say that the amplitude is simply going to be the absolute value of a. The book, always in their generic form, calls this coefficient in front of sine or cosine capital A. That's kind of helpful because it makes me think amplitude, but do be careful. Amplitude by definition is a distance, so it's positive, so it's the absolute value of that number.